So my charge for today, and please tell me if you can't hear me, but my charge for today is to talk to you about landslides and the geology in landslides. And what I'm going to hope to do is just give you a quick kind of review summary so that you really have a way to grab onto things as you're listening to the rest of the discussions here today. It's really easy sometimes for me to teach geomorphology because I start teaching it generally in spring. So in January, this is from about 2 years ago, there's usually a big old landslide impacting someplace in the Pittsburgh area. And I can show it to my geomorphology students and say, see, look at all this. You could have a long and vibrant career in landslides. And thinking about landslides, mitigating landslides and all of this. This is a picture of the Route 30 landslide. You probably will hear about this at some other point during the course of these seminar series. It was a big slide. It was a big problem. This is a picture from the Post-Gazette. So what I'm going to try to do is talk about how the geology and how the local terrain and hydrology sort of come together to create landslides and how we think about them in terms of on a broad landscape scale. So my research interests have to do with how erosion and sedimentation create changes in the sediment dynamics at the landscape scale. So we use tools where we kind of simplify the landslide and then we look at it across the entire landscape. And I think that this simplification will literally allow you to latch on and think about how some of these other more site-specific investigations have worked. So if you're lucky in your coursework, you probably have seen something like this. This is a classic kind of diagram. This one is from Ritter. It's a geomorphology textbook. So you take all the different kinds of landslides that are available and you try to put them into categories and try to come up with similarities so you can think about them in a more systematic way. And what I want to do is, if this is your only exposure, let's start taking a look at this exposure and think about what's important for landslides. So we can zoom in on this figure, and we can look at the part where you just have the slides here. So this is the slide section of that figure. There's other things we don't have time to get into that in 15 minutes. So immediately you can see that the composition of the materials that are sliding is important. It changes the way the materials slide, it changes the way they end up, things like that. You can also, from a quick review of this, see that the slope is very important. And both of these, just from our looking at a first sort of simplification of sliding and mass wasting, comes up with, two important kinds of things. And let's talk first about the slope. And I want to share with you another figure. This is a classic. It's the earliest I can find. It's a Harper's paper in 1997 of how the three rivers have evolved due to the glacial melt events over the last 100,000 years. That's not quite as far. I mean, this concentrates on the most recent ones, but you can see that, at some point, we don't really have a good idea of what this landscape looked like a long, long time ago, but we know that there was substantial melt water draining through this area due to the melt of the continental glaciers. You had a big incision and vent. You cut deep into that valley. Later on, as they continued to drain and they brought sediment through, you laid these sediments that form the basis of a lot of important regional groundwater aquifers. But what I want to do is I want to focus in on this. And I want to talk to you immediately about
Sorry, Dan, you're muted there.
I got it. I just unmuted myself. This is an unusually rugged area for sitting in the middle of the continent, and it's because of this deglaciation. And it doesn't just affect these main rivers. You you actually can, these propagate up through all of the drainages. So the drainages are also not necessarily, but are pretty steep comparatively. So one of the reasons we have a lot of landslides in this region is sort of this glacial history. You'll see this again and again. And also Mount Washington, another famous sort of landslide problem area you'll probably see as you continue through the seminar series. The next thing, though, I want to do is talk about this. So in this conceptualization, and this is just to simplify to allow you to look at the rivers, but think about what we're thinking about how the geologic materials are made up in the non-river sediment, non-incised areas. Similarly, if you go back to this diagram from Ritter, you can see, we tend to think of these things as very, very homogeneous masses that are moved. And, nothing can be further from the truth. This is the figure that my students probably make fun of me for always talking about. This is a figure not necessarily developed from landslides. It's the Sheet and Kozar model of hydrology on the Appalachian Plateau. They're thinking very much about coal mining impacts, but this applies throughout. And one of the things you'll see is you have these redundant strata of sandstone, limestone, shale, siltstone, however you want to cut it, that make up the majority of the underlying material underneath our soils and underneath the sliding materials. And this has redundancy is a virtue. So what it means is it's really hard for water to take the kind of traditional flow path you might see where it recharges at the ridgetop, goes deep, then comes up and discharges to your regional surface water drainages. You get a lot of short circuiting of that. You get flow that pops out on the side of the hill slope. And this is very uncommon, and I will show you just an example of the errors that has caused me. So I was trained in Baltimore in my ideas of hydrology. I saw a hill slope. I also work in urban systems, so I want to keep this kind of expensive data logging equipment undergrade so people aren't playing sensor baseball with it. And we installed this on a hill slope. This was one of the first instrumentation projects because we thought, it'll be nice and dry, well drained. We did it in the summer, and this is what happened as we wetted up, in October, this time of year, as we started to turn off ET, wetting up the thing, and fried our sensor, and we spent years trying to keep ammo boxes, anything to keep water out of this material. I learned a lot in that instrumentation, but you'll see in a second that water popping out onto your hill slope is also going to be very important for how these things, the risk of these things moving. I'd be remiss, so there's other things, there are specific components in this stratigraphy that are worse at holding their shape and more prone to start to deform than others. The famous one is the red beds. You're going to hear a lot about that. Here's a map from the PGS landslide fact sheet that shows where red beds are bedrock, or where the bedrock is sitting on red beds across Pennsylvania. You can see we're here in Pittsburgh, Allegheny County. It causes big problems. You'll hear about this other times, but I also wanted to give you this visual clue because I think that we all talk about red beds, but we don't think about what it looks like. If you're out looking at your field site and you see this, and you're considering the stability of the slope, I encourage you to look very carefully. And then for the last part, I want to try to put these all together into some of these, like I said, landscape indices that we use to try to understand when and where you might be at landscape risk. So what we use are a series of models that are based on the assumption of an infinite slope. Not a great assumption, but it works. It simplifies things. And what it says is this slope goes on forever. You don't have edge effects at the top of your slope. You don't, at your ridge line, you don't have edge effects at the bottom of your slope when you're getting towards the toe or the surface water drainage. So you don't have to worry about, the details of the geomechanics in these areas. You can concentrate on what's going on in the sliding area. So a typical landslide might look like something like this. The slide material pulls out and then is deposited further down the slope. And I'm drawing this for you because this is more like what a slope would look like. There's probably a lot of exaggeration in terms of the vertical, but I want to show you this because it allows you to understand this geometry I'm going to be showing you throughout the rest of this talk. So what we do is we consider this landscape scar, the materials that slid, as a trapezoid, or a parallelogram, excuse me. And it looks like this. This allows us to use trigonometry to sort out the forces. This allows us to, come up with our masses of material. And this is a unit width rendering, so you can imagine that this landslide goes into and out of this screen. So the depth of this slide material is defined by what we call a failure plane. And the failure plane is defined by where the scar exists. And this gets tricky because you can have different places in your soil or your sediments that are sitting on your landslide prone area that can slide. So you could have, in some conditions, this could be a failure plane. In some conditions, this could be a failure plane. So you end up starting to spend a lot of time thinking about where your failure planes are in multiple scenarios of failure planes. So it becomes hard to predict. The best way we probably do it are things like looking for contacts between geologic material where we know there's historically been problems. So we look for the red bed as a contact, and that can be a failure plane. We look for other things that can be failure planes. And then the next thing we sort of think about is, so going back to this idea of slope, at what angle does failure occur? We can do this from first principles, and we can think about things like sand pile experiments where we don't have wetness, we're just taking dry sand and we're sprinkling on the top, and your failure angle tends to move somewhere around 45 degrees. As you saw in that first picture, as you'll see through the rest of this seminar series, we're not dealing with dry sand in the Pittsburgh region or anywhere where we get lots of landslides. So what we have to do is we have to think about where all the other landslides are. And I really am glad that Tony accentuated the historical nature of this, because, there are these, documents that when you're thinking about landslides in this region, you go to again and again. There's a whole series of USGS papers by Pomeroy. This is just an inset from his set of insets from his 1982 report. And you can see there's landslides, historical landslides, active landslides. I just wanted to point out this is US 30. So these problem areas occurred again and again. Here's Washington Avenue as you go down and turn left to go to the zoo. But what you do is you look at all the active landslides and you say, oh, okay, at about 30 to 35 degrees of slope, that's where most of our landslides are mobilizing. So what we want to do is get a better idea of that cohesion. That dry sand is one case, it's a cohesionless case. We have to start figuring out what's the role of cohesion in keeping these landslides stable. And cohesion is how sticky materials are to each other. So you've got friction that, you generate heat when you're rubbing them, but there's stickiness, which is actually a more, it's stronger than simple friction. And what we want to know is what is the cohesion that's going on here. And so you can go in and do lots of things. You can take core samples. You can come up with ideas of, my timer's going crazy, excuse me. You can take them, put them in a triaxial apparatus, figure out when things start to fail. But, the bigger cohesion problem is one we really don't have a good handle on is the role of root cohesion. So here is a tree and it's clip art. And you can see if you put these roots across a failure plane here, a potential failure plane, that failure plane is going to be a lot more cohesive than the failure plane we're showing down here. And the state of the art for measuring root strength and really is you go out with a a meter and a come along and you crank on that root until it pops, and then you try to come up with an idea of what that cohesion is. So there's a lot of uncertainty still in there. And when I say uncertainty, all of you who are students should think about that being your job. So and the other thing, that being a place where you can spend a career defining things. Here is a reminder that most of our slopes are forested because it's hard to build on them. So this role of cohesion can be very, very important. The next thing I need to speed through is water. If these are dry sediments, there is less friction down here. There's less weight pushing this against this. There's less driving force pulling these sediments down. As you fill the pores, changing this from dark to blue, you make this heavier. And so both of those forces increase. But the other thing that happens is you add some buoyancy to these sediments. So they float a little bit in the water. And what we do is we organize these into factors of safety. This is the SynMap equation. That's for stability index mapping. And we take a look at this resisting force and the driving force, put them in equilibrium. So we have the cohesion. We have this regional angle in the upper part. We also have, we define our angle of our slope here as theta. This is our depth to our failure plane. So we have the mass of the sediments. You can see, I told you we needed to do this for the trigonometry, the density, less the buoyancy, the mass of the water. So this is what's holding the sediments. This is what's driving the sediments. So when you have a 1, you're about the same. The problem with this is you can be quasi-stable. These things can sit with a factor of safety much less than 1 for a very long time because it takes a little jostling to move them. And I want to show you another of my favorite examples. It's not local, but it's just mind-blowing to me. This is a Landsat image from the USGS Earth Observation System of Hokkaido, the northern island of Japan, in July of 2018. And soon after this image was taken, Typhoon Jebi came through, really got that area wet. And then there was a 6.6 on the Richter scale earthquake. So when you came back and looked at that same area in September of 2018, you can see all of the landscape scars across the surface, just back and forth a couple times. They actually have a nice slider in the USGS Earth Observation System to talk about this. But if you perturb the system, you can set off a landslide that is quasi-stable, which makes it, again, hard to predict. Let me just summarize. This prediction is hard. You know, we have multiple planes to look at. We don't have a good idea of what the cohesion is. And this is further complicated by the fact that the fine root cohesion is much more important than the thick root cohesion, and we really have no way to do a come-along analysis on that. Figuring out how much water in these wet hill slopes is around is a problem. And this is, you know, again, I work in urban systems, so this is a particularly big problem as you have deteriorating infrastructural systems. You can get water in really unexpected places. So hopefully that gives you a framework to think about why people are talking about context, why people are talking about water, why people are talking about all the things they're going to be talking about and characterizing in the next 2 weeks.